Next, we have Fatima Savok from University of UMass Dartmouth as well. So, thank you.
Hello everyone, I'm Fatima and I'm going to talk about the application of recurrent neural networks to covariate software defect prediction. To provide the background about the subject that we are going to talk about, that I start with the definition of the software reliability, which is a probability of failure-free operation for a specified period of time. And we can raise this reliability with predicting future faults as a function of testing time or effort to improve maintenance scheduling to avoid future defects. Previous studies applied non-homogeneous Poisson process NHPP to software reliability gross models. They are good, however, they are parametric and they may not be able to catch all the defects. So just we introduced recurrent neural networks and its variation, long short-term memory, in order to predict the defects. Results suggested that neural networks are able to track and predict the future faults, specifically 6 and 9 times reduction in prediction error than covariate SRGM. As a quick review on covariate software reliability gross model, I start with the mean value function, which is the predicted number of the failures up to and including the nth interval, in which the omega shows the number of the defect discovered with infinite testing. And pi here is a probability of a defect discovery in the ith interval, and can be calculated using this formula, in which xi is the covariate associated with yi, theta is a vector of the model parameters, and beta is a vector of covariate coefficient, and h indicates the hazard function. We used two neural networks. First, a recurrent neural network, which is a type of artificial neural networks that allows information from prior inputs known as lookback period to influence the subsequent input of the same node and consequently the output of the neural network. However, it has some limitations, and we use a long short-term memory to address a part of this kind of limitations. And it is designed to capture long-term dependencies in sequential data. So we just introduced 5 different goodness of fit measures in order to compare different models, the traditional ones and the neural networks numerically. We have mean squared error, MSE, which is the average square difference between predicted and actual values. Predicted mean squared error, PMSE, which is the sum of squares of the prediction residuals for the test part. We have mean absolute percentage error, MAPE, which is the error as a percentage of how the predicted value deviates from the actual value. And we have predicted ratio risk, PRR, which penalizes the difference between the predicted and the actual number of the defects, where underestimation is penalized more than overestimation. And the last one is the predictive power, PP, which is the error of distance between the estimated and actual number of the defects and penalizes the overestimation. To illustrate the applicability of neural networks to covariate software defective in discovery, a new data set was generated based on the DS1 data set with 3 covariates. So this hypothetical data includes 3 covariates and the corresponding number of failures for each interval. And this generated data set is used as an input for different models. And here is the table that's achieved using the goodness of fit measures. We use different traditional models, covariate NHPP models, using various hazard functions, including geometric, negative binomial second order, and S-shape. And as you can see in the table, the bold line shows that LSTM outperform and achieve as better goodness of fit measures, such as approximately 6 and 9 times smaller MSE and MAPE, respectively, compared to the traditional models. And this is the visualization of the two neural networks that we applied. From left to right, this is the RNN, and the next one is the LSTM. You can see some fluctuations in RNN and a better model fit with LSTM. And this is a visualization of the comparison between the covariate traditional models and LSTM. The best model fit among the traditional covariate models achieved by S-shape. However, LSTM with the green lines completely match the actual data. So, to conclude, this study presented recurrent neural networks and its variation LSTM to predict the covariates software defects, and the results were compared with the traditional models. And the results, the numerical results shows that LSTM outperformed compared with the covariates NHPP models. And as a future research, we suggested to examine the effectiveness of feature selection methods to evaluate the stability of RNN and its variations on more complex data sets, including more covariates. Thank you, everyone. If you have any questions.